implicit score that would represent this relation. And then you can say, okay, then we can go back. Yeah? So this is how the proof of the theory works. You don't need to know the score, but it exists. Yeah? Existence, then you get all the properties. Some couple of experiments. Here we made a very simple artificial classification problem, which was just two Gaussians. And we took a state-of-the-art transform and we made an oracle. And the oracle gets an instance or gets two instances from the data generating process. It says, okay, this is not conforming to this one. And it only gives this preference feedback to the learner, and the learner then has to infer it needs to, let's say, replicate the score. Yeah?
有挺多的，加起来应该有20多个吧，不算多，不算多。就是 conformal prediction， 讲那个不确定变化 conformal prediction， 就是有一年的那个 ICML 的最佳论文的相关。
他了解 conformal prediction， 做那个
calibration， 你们做 calibration。我们就是这个有一个集合，就叫 calibration 集。
calibration 赛就是我们用来做 calibration 的。
其实我只是去做，它是跟 training 集合是高度相关嘛，但是不一样的。
所以是直接是就是你是不是一个 post hoc 的 method， 你是直接就是顺着这个 conformal 的一个 model。
不是，我们是这个 model 是训练好的，但是训的过程中的一些东西，一些 information 会给到那个 conformal prediction。我们下一步会像你说的，就是把那个 conformal prediction 塞到那个 training 里面。
他了解这个。
The same stuff as certification, you can compare, it's not super interesting, but it works similar. Yeah? What we expected, so this also not super surprising, is more of a proof of concept. Yeah. And in this experiment, we made a mixed setup. If we have, for example, 100 pairwise comparisons given, we can use them with this approach, but not with this. This is basically, if we have a label, some classification images, yeah? For example, an image with a pen and the label pen. Then we retrieve this image with pen, is preferred over this image with dog. This image with pen is preferred over this image with gorilla. We basically break down the classification data and we work with that. Of course, we wouldn't do this in practice. Just to show that it works. Yeah? So in practice, you would already start with preference data because this is the thing you could collect. But this is just meant to show, okay, if we use classification data and we retrieve some preferences, then we also perform similarly.
Both of us, yes. Conformal prediction, both of us, yes, all of us have conformal prediction. It's a kind of new uncertainty quantification method. Yes. So we need the uncertainty smaller, the better. So it's represented by rigid, lower bound and upper bound. And we need the bound is smaller. And previous work is fixed, and so it's the same for all data. But we use residue to make sure the bound is differently according to how the data looks like.
Yeah.
So it's reasonable, right? So it's better than basic baseline model. And besides, we use two separated GNN to train. First is for the prediction, and the second is for residue. The residue.
It's a regression.
Yeah, both for regression and classification.
Actually, I come from the different.
What kind of data is it?
Most of them are graph. Traffic, election, and others like Quora, or something like that. How about yours?
Mostly horizontal. Yeah, but I know about the maybe you have some. So can you compare with some other methods?
Yes, first is the Jiajun Fuller, 2020. And another like CF and CG and CPR. You can check it out. Also, I will upload some video on YouTube.
Like showing the results.
Yes, yes. Can you hear me or write my also code.
Then the sets are better. And then the proof is also quite simple because with these properties numbers, then you can show that there also exists a score. Yeah.
特别大，不算特别多吧，20-30个。对，应该还不
完整的讲一遍，这个20-30个完整的讲一遍。
完整的可能10几个。
太多了，好累。
就是所以到时候就你讲的时候可以多准备点，多准备一点吃的。
多准备一点吃的。
你到时候讲的时候啊，我建议你。很累，喝的水。啊。
When it's interesting, if you have this type of data, and you have a lot of this data, then it's basically not much of this data, then you can basically show what
然后这边其实感觉人没有那边多。
这边必须这两个。
好像那里面也是。我到沃少。
viewing
prediction is a new method for uncertainty quantification. It's popular nowadays, but there are some questions. For example, nowadays the work. First, we want to learn a region for the uncertainty.
Okay.
Lower bound and upper bound.
Okay.
But nowadays, the previous work usually have the fixed parameter
Okay.
for all data.
Okay.
It's not good.
Okay.
So our work learn according to the data.
Okay.
So learn the residue. Besides, when we learn the residue, we set a separated GN model.
Okay.
Yes, this works. So this work well, and
This is a residual for what?
for
error?
residue for error. Yeah.
Error in what?
Error between the prediction and the ground truth.
Okay. Okay.
How about
Residual adaptive. Thank you.
you can check it out. Maybe paper or code. And you can keep my part.
Sure.
I will send some, upload some video on my YouTube channel about pursue PhD or something like that, writing paper, come out idea.
Thank you.
More prediction. More prediction. Is this up?
Well, okay, we have like GM. Do you want to perform a prediction? Residual relay. Okay, what's the reason? What's the purpose?
The purpose is want to get region. This region means our prediction is highly related, highly located in the region. Usually 90%, 95% in this region.
95?
95%.
Yeah, okay, like two sigmas.
Yes. But nowadays the model usually have error, big error, because the lower bound and upper bound is not good. Our purpose is to make the upper bound and lower bounds smaller, but at the same time cover 90%, 95% of the prediction. Yes. Oh my God, this guy. To do that, we first learn the residue. Is varies according to how data is good. So it's not fixed like a previous work. It's reliable and feasible. It's changeable and changeable according to the data. So it's more reasonable and reliable.
So what we have?
We learn two models at the same time. First is for prediction and second for residue. For the error. Use a separate model. Learn the residue. Yes. The idea is from intelligent control theory. It's like elective reward in control system, control theory.
We have like another regime. Is it should it be like very light?
Very
The
light.
second way, very light. Light model. Compare this one.
Compare one is lighter. Yeah.
Light, yeah. Because I know, I think previously it could be done even without model, but just by just gradient descent or something like that to compute noise. As I understand, you add the model and try to model the noise with the model instead of just gradient descent. But I am still thinking that it should be very light because you cannot use like very heavy.
Yes.
Okay, and yeah, it is understandable. So what's the result? What was the difference?
Results.
First 17.
Yes. First, this coverage is around 95%, and then the interval is much better.
And, do you have the noise, the initial noise for this?
Noise, yes. But the noise is generated by ourselves. It's not generated.
High level is enough. What we do before prediction is we get a new test instance and then we want to confirm the prediction test. And we want the prediction test to be valid. Yeah? So if you specify probability, we want that the true label
What is
set.
Got it.
Okay, so we need three ingredients.
Is ID is test load.
Can we also be regressive?
They are around the
Why do you think is around like minus 0.5?
We need a non-conformity score function.
This have to
This is basically
Is
score the new data points. I'm getting the data point
reordered
with
and
the score and then tells you both conforming and non-conforming. Yeah?
this is meeting and this is the prediction. Region prediction. Around 95% is region.
To tell how non-conforming
95%.
and a very simple example is this lag score.
Okay.
Just uses the counter probability.
Here.
Okay,
So,
so
for example, you get a new data point and you say,
Yes,
okay, let's
yes,
say this is a
but,
cat, and it then says this is non-conforming 1 minus the probability
here,
that I think this is a cat.
okay, so let's say we
5% is here and this is there. 95% is
then the non-conforming score
in
is 0.6.
0.5 feature.
And so the
Yes.
the interpretation of the non-conforming score is
I'm
how
wrong.
likely it
I'm
is
wrong.
to be wrong, or how likely it is
This
to
number.
like give you a
Yes,
set,
yes.
maybe?
The interpretation would be how
This
conforming is it to your
how long
calibration.
this number and how many in the
The data generating process, they do
We
not
can adjust like both. If we choose, if we fix one, the other, like, we choose only one. The other is dependent from the second parameter.
yes. Usually
How do you
control
adjust
this.
p-value.
But usually done by setting alpha.
So you found both hyperparameters this to be in that way, because if we, for example, choose one, the other can be found.
And you say, okay,
And somehow, but we have interval and we have like bound.
and then you look in your
We look
calibration
at bound
data
and we
where
understand what
The bound is generated by model, not our setting. We only set the alpha.
Yeah, I mean,
So you're sort of
okay, I
using
got it.
this is like your decision.
This is
So you choose like about around 95% and look what the number of
So it's 1 plus the sum of if the conformity score.
the length of the
This is the new
interval
data
is.
point.
yes.
the new data point hypothetical label.
Yep. Oh, so right, because you said you iterate over all the possible labels.
See you later.
What's the value per label?
Yes. Okay, and for each possible label, you check if it's greater than or equal to alpha.
validity guarantee. Okay, so just for validity, the two one will be
对，直播，
啊？
可以直播一下。
哦，你在直播？是什么 ？YouTube？
YouTube。
可以啊。
对。可能就是宣传工作嘛。
不错不错不错。这个不错。还是要
对，做宣传，帮组里做宣传。对。
这如果是你们组账号，那继续。因为我想要看这个，我想要看。
哦，对，手机可能这个，我这个第一次就不太熟，好累。但是我帮您宣传都行。
So you order all the labels, is that right? Yeah. And then you have a new data point.
On the computation of 15 values, you don't need the value of the score, only the relation. Only how many are before, how many are behind. This you can perfectly do with the relation. So given the binary relation of x times y, we can do performance prediction.
So just by using, instead of actually looking at the score, just learning where its relative position is, like among other like potential labels, you can still do it. And what is complete translation?
Complete means that on the whole space x is defined on the whole space x times y.
Okay.
Trivial.
Yep.
Transitive means
If A is bigger than B and C is bigger than B, then sorry, something like this, something like that.
if A is preferred over B and B is preferred over C,
A is preferred over C. Okay, that's standard, right? I believe that.
exactly. So this is what you need for an ordering. And continuous is basically
It's okay.
A bit technical. You may even leave this out. It still works for both cases. In very synthetically constructed cases like electrographic ordering and so on.
Like you need time rating.
Yeah, exactly. And then if this holds, then you can the same guarantees as this. The proof of this theorem is actually quite easy because if this holds, then there's a result from economics, which says then there is a real number and you can order on the real number. So there exists the score. We don't know the score anymore, but it exists. And if it exists, then we have the same guarantee.
Sure, because fundamentally, like here, you just care about who's where and
Exactly, right?
So instead of learning like a score function, which can be really hard and complicated, let's just learn something that gives you a correct order. Like, we don't need to be as fine right now.
So, the typical use case is this when you have data of this kind, yeah? So we have data, not with these hard labels, and you say, okay, this image is a dog, but when you have this reference data, this image being a dog is more likely than this image being a cat. And it must not even be the same image, yeah? It could be this is more likely a dog than this is a cat.
So instead of like having like an image and a label in your train data, you have, what do you have? You have like an image and an Uber data.
Like that, yeah. But it could also be two images. It could also be this image being a dog is more likely than this image being a cat. But critically you have the same instance, but it's not restricted to this.
Sure. And this is the last function?
This is the last function we use, and so this is what we learned in the gradient theory model. This is already know this in the preference learning. Okay. It's also used a lot in this LLM fine tuning and so on. So what it basically does is it learns the utility function, and this utility function is basically ordering the alternatives. And it's a bit more involved than training a standard text line because it's always on soup
situation would a researcher use preference space instead of vanilla?
You would use it when you have preference data.
Oh, okay. Okay, got you. Okay, okay.
So if you have, for example, if you also have a lot of preference data,
Got
for example,
you.
you use but only a small amount of hard labels, then this will kill it. Because the hard labels you can also convert into this.
That is true.
You cannot convert this into this.
That is true. So when your data is less certain than having rank labels, then with a little more computation cost, you get the same thing.
Exactly. Then you can, if you have only the weak supervision instead of the strong supervision, you can do it.
I see.
Then we did a couple of experiments and it works. It works.
Okay. TLDR experiments work.
This is maybe the most important.
Yes,
Because this is exactly where we did it. So we have 100 pairwise comparison, only our method. And then we have standard labels, standard hard labels, in a varying amount. Of course, we start with this advantage here, and then this diminishes as more classification data becomes available. And the classification data can be used by our method and the others. The preference data can only be used by ours.
That's right.
So this is why we have this advantage here, then it diminishes get more
As you have more data, then this guy will perform.
So we never